This is a revision video for the GCSE Chemistry topic of isotopes and relative atomic mass. If you're studying A-level chemistry and you want something a bit more in-depth and with some harder calculations, then have a look at my A-level chemistry playlist and there are 2 videos on this topic. If you are here for GCSE Chemistry, then before we start, pause the video, and in the description there is a link to the accompanying worksheet, and also make sure that you have a calculator because unless your mental maths is very good, you are going to need it. In this video, we're going to recap what we mean by isotopes, and then we're going to look at some different ways that we can calculate relative atomic mass from abundance data of different isotopes. First, let's define what we mean by isotopes. This is an important term because it comes up in both GCSE Chemistry and GCSE Physics. Isotopes are atoms of the same element that have different numbers of neutrons. Now, because they're the same element, we know that they must have the same number of protons, because that's what defines an element. I've got 2 atoms here that both contain 3 protons, so they're both lithium, because any atom containing 3 protons must be lithium. We know that in an atom the number of protons and electrons is balanced. They always have the same number in an atom, and that's why atoms have no overall charge. So it would be true to say that isotopes are atoms of the same element that have the same number of protons and electrons, but different numbers of neutrons. Now, in terms of their properties, the chemical properties of an atom, how it responds to other elements, those are controlled by the number of electrons and how they're arranged. So where we have different isotopes of the same element, they will always have the same chemical properties. But their physical properties, such as their density and their melting point and their radioactivity, those will be different. If we're going to calculate relative atomic mass, then first we need to define some key terms. An isotope's abundance refers to how much of it there is. So in an exam question, they're going to give you 2 or maybe 3 different isotopes, and for each one they'll give you a number to represent how much of that isotope there is. That's its abundance. The atomic number is one of the 2 numbers given on the periodic table, and it refers to how many protons an atom has, and that is what defines which element it is. The mass number is the other number that you're likely to see on a periodic table square. For a particular atom, the mass number is defined as how many protons and neutrons it has. The relative atomic mass is similar to the mass number, but it's not for a single atom, it's for an entire sample. So if you have 2 different isotopes, then the relative atomic mass won't be an integer, it won't be a whole number. Here's an example of a typical exam question. A sample of boron contains 25% boron 10. That means the isotope of boron that has a mass number of 10. And 75% of boron 11. What is the relative atomic mass? Now there are a couple of different ways that we could approach this question, but I'm going to show you the longer one first because it's the one that will always work, whereas the second one will only work where you have percentage data. We do have percentage data here, but you might as well know the long method that will always work. So to calculate relative atomic mass, I take the mass of my first isotope and multiply it by the abundance, and then the mass of my second isotope and multiply it by the abundance, and then I divide by the total abundance, so the different abundances added together. It's possible that in an exam question you could have 3 or 4 different isotopes, in which case you would just carry on multiplying them by their abundance and dividing the whole lot by the total of all of them. So in this example, I'm starting out with mass numbers of 10 and 11, and I'm multiplying them by abundances of 25 and 75. And obviously because those are percentages, they add up to make 100. If I multiply out each one of those, I end up with 250 plus 825 divided by 100, which is 10.75, and that's my final answer. At this point, I would always suggest that you do a common sense check. Your final answer for relative atomic mass has to be somewhere between your lightest isotope and your heaviest isotope, which here it is. You're also expecting that it will be closer to the isotope that you've got more of. So here my final answer is closer to 11 than 10 because I've got more of the isotope that has a mass number of 11. So I did say that there's a faster way to do this calculation, and as long as our abundance data is given as percentages, then there is. Rather than timesing by 25 and dividing by 100, and then timesing by 75 and dividing by 100, I can just speed things up a little bit and either multiply by a decimal, so 0.25 is equivalent to 25 divided by 100, or even use the percentage button and multiply by 25%. and doing each one of those would get me the same answer that I got from my longer calculation. Now it's your turn to have a go at some of these calculations. Hopefully you've downloaded the worksheet from the link in the description, so you can pause the video and work out what the relative atomic mass of each one of these samples is. Good luck! So these are the correct answers to the last 10 questions. Hopefully you've got them all right. Thank you for watching, and I hope this video was useful to you. Don't forget to like and subscribe for more GCSE chemistry videos coming soon.